Good morning. I do want to make this very clear before we begin that this chapter is going to be a little bit different from the other ones that we've done. The other chapters that we've done this year so far, all of them we've had some experience with what we're learning in Chem 1. The last chapter that we did, thermochemistry, thermodynamics, we did delta H and S and G in Chem 1. So you already knew something about those. Before that we did gas laws, you already had known that. Before that was reactions. Before that was stoichiometry. Except for organic. Organic was very different too, and you didn't have anything in your brain already. So this chapter on kinetics is completely different. I don't think anybody has any experience with kinetics, and I think you're going to find it to be a little bit confusing and frustrating for the first couple of days. Because we're going to be doing things, I'll be talking about the order of the reaction, but you're not really going to know what the order of the reaction means or what it does for us for a few days. So until we have enough in our brain to start attaching things together, it may be kind of frustrating. So just I want you to know that right off the bat, that it is going to be different and a little bit confusing, I think, until we can put everything together. This is where we ended yesterday. We were talking about how do we measure the rate of a reaction? Well, we could measure it by looking at the rate of the reactant depletion, and that would have a concentration versus time with a negative slope because the reactant is getting used up. Or we could look at it in terms of the product formation, in which we start with 0 and it goes up. This implication is a 1-to-1 ratio, so the rate that this is going down equals the rate that that's going up. However, what if we don't have a 1-to-1 ratio? What if we have one of these going away and one of these is being formed and going up, but two of these are being formed? Well, the difference in this case is as A is going down, B is going up at the same rate as A is going down, but C is going up twice as fast as A is going down. So we can use the balanced equation and the coefficients in the equation to determine relative rates. If you're given one, you can determine how fast the other or some other substance in the equation is changing. Okay, I'm going to just go off of that slide, show you a couple of examples that are in the book. 23 and 24 work well. Okay. Take a look at 23. We have 4 pH3s breaking down to P4 and 6 H2s. It says, if in a certain experiment over a specific period of time, 0.0048 moles of pH3 is consumed in a 2-liter container each second of reaction. So usually the rate of a reaction is determined in molarity per second. How is the concentration changing over time? Did you see that, molarity per second? Okay, so if you know how many moles of pH3 and how many liters there are, you can find the molarity, and then it says are consumed each second. We can find the molarity per second for this thing. We can find the rate of the reaction. With respect to the pH3, what are the rates of production of P4 and H2 in this experiment? So once you find this thing, what would be the rate of production of P4?
Divided by 4.
Yeah, it would be 1/4 of the consumption of pH3. Because it's a 4-to-1 ratio. Every time 4 of those get used up, 1 of those is made. So this goes up, but not as fast as those are going down. Okay, 1/4 as fast. What about the H2?
3/2.
It would be, yeah, 6/4 or 3/2 or 1.5 times as fast. So this would be made faster than that's going away. So the relative rate is pretty simple. We'll take a look at number 24. What is the relationship between the rate of production of ammonia, that's the NH3, and the rate of consumption of hydrogen? So ammonia is being made faster or slower than hydrogen is being used up? Slower, right. So whatever the rate of hydrogen being used up is, that times 2/3 is how fast ammonia is being made. Yeah? So use the coefficients in a chemical equation with respect to rate the same way you would use stoichiometry. Okay, with the balance of the coefficients. Now this slide I know has a lot of words on it, but this is going to get us into a statement that relates or describes what's happening throughout the reaction, and that we can gain some information about what the rate of the reaction is. There's two different rate laws that we call them. There's the differential and the integrated. I warned you about those yesterday.
Yeah.
We find the differential rate law if we know the rate and the concentration. We can find the integrated if we know the concentration and the time. So remember, concentrations are changing. We'll have two labs that we do. One of them will find the differential rate law. The other one will find the integrated rate law for it. Now today is kind of slow. It's this lesson is like walking through wet cement. Once we get through today, I think everything is going to go much faster. I think you're going to find this to be interesting and enjoyable, this chapter. I really like doing the kinetics chapter. But at first, it doesn't seem very appealing. I get it. Stay with me. I don't want you to join Trina there. Yeah?
I was just wondering, so we're doing everything into like catalysts? Kinetics?
We will.
Okay.
Yeah, we're going to talk about catalysts and what a catalyst really does to speed up a reaction. Yeah, we're going to get that too. Very good. If you have a highlighter, or if you have maybe a different color, whatever, this middle of the 3 bullet points, both must be determined by experiment. You can't look at a chemical equation and know anything about the differential or the integrated rate law. You have to run the experiment lots of times, changing the concentrations of the reactants to figure out what's the pattern, what is the relationship between concentration and the rate of the reaction. So that's probably the biggest misconception in this chapter is even when we're done with the chapter, people still want to look at the chemical equation and try to determine how fast the reaction is going or write a rate law just based on the equation. You can't. You have to use the data from experiment.
So I like these bullet
Just the middle bullet.
Oh, okay.
Steve and Andrew, that was the nicest gift anybody's given me. I have such warm hands now. Yes. Yep. And anything else you want. Okay. Now, I'm going to jump over my notes. If you have printed the notes out, they're going to go through several slides of differential rate law. We're going to start with integrated rate law because the lab that we do on Thursday is going to have integrated rate law in it. So we're going to go through that first. You'll have to see. The differential rate law looks like this. This is the general form of it. It's always going to be the rate equals some constant. It's a lowercase k, different from the equilibrium constant. It has nothing to do with equilibrium constant. That's a capital K. The rate constant, K, times the concentration of the reactant to some power. The power is going to be called the order of the reactant, the order of it. It could be 0 order, 1st order, or 2nd order. I've got something about 0, 1st, and 2nd up there. That's integrated rate law. It looks different when it's in a differential rate law, so just be aware that differential rate law looks like this. You're going to actually see this as we derive something from the integrated rate law. So I'm just going to skip this for right now and go to slide 19. There it is. So here's the deal with the integrated rate law. Remember that concentration versus rate is going to give us the differential rate law. Concentration versus time is what we're going to need for the integrated rate law. It is more tedious to do the integrated. That's an advanced warning. Tedious, believe me. So I have an example equation. This is a decomposition reaction. And I want you to assume that it has been found that it's a first order reaction. I'll tell you what first order means in a second.